Looking at Leetcode number 40. It's a question called combination sum 2, and highly recommend looking at the other videos, combination sum and combination sum 3. My advice is to go from combination sum 3 to 2 to 1. We're going to be using a template, a backtracking template, to solve this problem, as well as all other problems on this playlist. And it's a very powerful way to solve any type of problems that are dealing with permutations, subsets, or combinations. So we're going to be looking at recursion, breaking down recursion and how it looks like on a tree. And so we'll go through that conceptually, and then we'll go ahead and write out the code. And it's really important to kind of make that connection between what the code is doing conceptually and what you're actually writing. Okay. All right, so here we're given a collection of candidate numbers, candidates, with a target number target. We want to find all unique combinations in candidates where the candidate numbers sum to target. Each number in candidates may only be used once in the combination. And we don't want any duplicate combinations. So here we have 10, 1, 2, 7, 6, 1, 5. Our target is 8. And we can see here that these are all the combinations that equal 8 without any of the duplicates. Okay. Here we have 2, 5, 2, 1, 2. Target is 5. And we can say we can see that we have these two options here. There's no constraints on the length of our sub result, but it does have to equal the target here. Okay, so let's jump into the conceptual and kind of see how we can break this problem down. So we want to visualize this as a tree, okay? And we'll go level by level to really kind of show you what's going on underneath the hood when we write out this code. So we're going to start at I, okay? And here, this is going to be our first level of the tree, and we want to basically add all the elements from I to J on the first level of the tree to our slate. Okay, so what does that look like? So we're going to have 1 that gets added to the slate, 1 that gets added to the slate. This is the breadth first search. So we're going to have 2, we're going to have 5, so on and so forth till we get to the end, which is 10. And all we're doing here is we're going to take a for loop in that first level, and we're going to iterate through our array. And we're going to sort it as well, okay? That's another thing. The input is not sorted. We're going to go ahead and sort it. And that'll make sense in a second on why we're sorting it. Now, once we get to this first level here, we want to figure out what do we want to pass into our recursive case that's going to handle our second level. So let's say we're here, okay, and I is over here, and J is over here. Now, if we add in our recursive case, J plus 1, what are we passing in here? We're passing in the index of 1. Okay, so what does that mean? In this next level, I is now going to increment here, and J will start wherever I is at. And in our slate, we have this 1. Okay, so now we're going to do the same thing as we did in the previous level. We're going to go ahead and add 1 and 1 to our slate, because that's where J is at. We're going to then go ahead and increment J over here, and we're going to get 1 and 2, 1 and 5, 1 and 6, okay, so on and so forth until we get 1 and 10. Okay, and all we did here was at this level we created a for loop, and we scanned this array, and we just pushed that onto the slate for this level of the tree. Okay, now at each iteration we're calling depth first search, we're calling our recursive helper, and we're just going to go ahead and put in J plus 1. So on this first level where I is equal to J, all we're going to pass in is J plus 1, and so so I will now increment here, J will start wherever I is at, and we'll go ahead and rinse and repeat. Okay, and so we have two cases. We're going to have a backtracking case and a base case. And we want to go down this tree as far as we need to go until we either hit our backtracking case or we hit our base case. Now, when do we want to backtrack? right? When do we want to get to a point in the tree where we don't want to go further down the tree because there's no candidates after that point are going to meet our base case, what we want, and that is the target has to equal 8, right? So if we get, let's just say, for example, we get to 1 in 10. The sum of this is 11. So no matter what we add, the rest of this tree, whatever we add to the slate, it's over the target. It's never going to equal 8, okay? And so because of that, we can backtrack right over there. We don't need to go any further down that tree, okay? Similarly, what if our leaf node here, I'll just write it over here, is 1 in 7. Now we hit the target, right? So if we hit the target, all we want to do is make a copy of this and push it into our result. Okay, so we'll just put 1 and 7 right here into our result. Okay, and then we don't need to go any further down the tree because nothing we add to it is going to equal 8. We already hit 8. Okay? So that's the idea behind this. I'm not going to go over drawing out the entire tree because with a number this big, it gets huge. But I highly recommend drawing it out yourself with a smaller input, maybe like 112 or 113 to really get an idea. Now, one more thing I want to mention is why are we doing I and J? So there's one more thing I want to mention is that is with repeats here. Why did we sort it? Okay, why did we have to sort this array? So I'm going to go ahead and clear out some of this here. And I want to kind of go over what happens when we're dealing with repeats, okay? Because that's another case where we can do backtracking, but we can actually do this on the recursive level, on the recursive algorithm. Okay, let me just go ahead and clear this out. Okay, I think it's going to be easier to do it that way. Okay, so here, clear this out here, clear this out. Okay, so now here we have 1 and 1, right? Now if we look here, let me go ahead and move I and J. Here's where I is at, and here's where J is at, right? And now if we look down this tree, what are we going to get? We're going to get 1 and 1 and J increments, right? Whoops. J is going to increment here, so we're going to get 1 and 1. We're going to get 1 and 2 as J increments, 1 and 5, so on and so forth. Now, if we look at this level right there, okay, this is where I is going to be here, and J is going to be here, okay? And so what are we going to get? We're going to get essentially the same thing on our slate. Okay, we're going to get 1 and 1, 1 and 2, 1 and 5. So here we're going to get repeats, right? And so what we want to do is we want to check if I does not equal J and nums at J, okay, nums at J is equal to nums at J minus 1, we just want to skip it. We want to backtrack right there and just go on to the next number. Okay? This is a little bit tricky if it's your first time looking at this, so make sure to watch this over and over again if you need to, or write it out with a pen and paper. Let's go into the code. We'll go over the code, and then I'll come back to this, and I'll show how this relates to the code. I think it'll make more sense when we get into the code. Okay, so here we're following a standard backtracking template. So what that is we're going to have a global result. Okay, and we'll set that to const result. Okay, and then we're going to sort our candidates. Okay, so we want to sort input. I'm just using a JavaScript sorting method here. And now we want our depth first search recursive helper. And we're going to have the input of I. We're going to have our array. We'll just call this candidates. We'll have our target. And then we'll have our slate, which will be an empty array. Okay, and so now with our template, we're going to have our backtrack case. We're going to have our base case. And we're going to have our depth first search recursive case. Okay, so this is the template, okay, and this is the same template I'm using to solve all the problems in this playlist. So just watch over a few of these and it'll start making a lot more sense. Okay, so our backtracking case, what do we want to do? We want to make sure that the target, we're not over the target. So as we make these recursive calls, we're just going to subtract whatever that value is that we're adding to the slate from the target. And so that way we know that if the target is ever less than 0, we have gone over. Okay, we've hit our backtracking case. So we can say if target is less than 0, we just want to return. There's no point in going down that tree any further because nothing we add to the slate is going to get us to our target after that point. So we can just backtrack from that point. What's our base case? Well, we can say if target equals 0, that means the sum of all the values in the slate equal the target, okay, because we're subtracting each value from the sum from the target as we go recursively down the stack. So if target equals 0, then we know we have a candidate that we want to push into our result. So we just do result.push, slate.slice. We want to make a copy of whatever the slate is, and then return. Okay? And the reason we're making a copy of the slate is that way we just use one array. If we didn't make a copy of the slate, then we're going to have to use a new array on every single node of the tree. So that's why we just use one slate array, and then we can just make a scan of that and push it into our global result. Okay, now we have our depth first search recursive case, right? And what we want to do here is we want to create a for loop with I and j and scan through this array and basically recursively go down the call stack, putting in these numbers into the slate. Okay, so I'll do for let j equals I, where j is less than candidates.length. And then we'll do a j++. Okay, so now we want to make sure we deal with duplicates, right? We know our array is sorted, so we want to say if I does not equal j, or if I equals j, I'm sorry, if I does not equal j and j minus 1 does not equal j, right? So if I, let's say I is here and j is here, okay? If I, which is 0, does not equal j, which is 1, because we're in the first index, and j at, the value at j, okay, does not equal, I'm sorry, if that equals j minus 1, then we want to skip it, okay? So we want to say if I equals, does not equal j, and candidates at j equals candidates at j minus 1, we want to continue. Okay? So what are we saying here? Let's just go over it one more time. We are saying if I, let's go ahead and put in the indices here just so it's really clear. 0, 1, 2, 3, okay. So if I does not equal j. J is 1, okay, and I is 0. They do not equal each other. And if the value at j is equal to the value at j minus 1, that means we have a duplicate. We want to skip it. We just want to we want to just go ahead and increment j to 2. Okay, so that's what we're doing on that line of code, because if we're dealing with that, if we are dealing with a duplicate, then we don't need to go down this tree. We can just move to the next one, because we're going to get the same numbers as we move further down. And then what will happen is we'll get a bunch of duplicates in our result, which is not what we want. Okay, so now what do we want to do? We want to add slate.push candidates at j. Okay, and then we want to call our depth first search helper. Let me just make some more room down here. We want to do j plus 1, pass in our candidates. Our target, what do we want to do with our target? We want to subtract whatever is in candidates at j. And then we want to pass in our slate, and then we just want to pop off whatever's on our slate. Okay, and so what are we doing here by this target minus candidates? That is a way for us to keep track of the sum, of whatever the sum is in the slate, because at every level we're just subtracting that off the target. And so if the target is less than 0, then the sum of whatever's in the slate is greater than the target, and we want to backtrack. If the target is equal to 0, that means that whatever the sum is in our slate is going to be equal to the target, okay, because we're subtracting on every level. It's just a way, that way we don't call something like reduce at this level, where we have to do a linear operation summing everything up on every single backtracking or base case. Here we can just do this with target, and it's much more efficient doing it this way. So once we do that, what do we do? All we have to do is call depth first search. We have our initial value of I. We pass in candidates. Okay, we pass in target. And then we use an empty array as our slate, and then we just go ahead and return our global result. Okay? And that's it. That's all we have to do for this. I know it seems like a lot, but the template that we're using here, I'm using the same template to solve all the questions in this playlist. And if you are familiar with the template, or you have this template down, you can see that you don't really have to think about much, except for, this case right here where you're dealing with the duplicates is maybe something that you might have to think of adding to the template. But this idea of subtracting from the target, making sure we have a base case, it's all just part of that template. So it makes solving these types of problems much, much easier when you're working with some sort of template or some sort of framework. Let's go ahead and run this, make sure everything works, and we're good. Okay, and we're getting pretty good time and space complexity. So let's actually go over the time and space complexity on this, just to make it clear on how to kind of figure that out. So I'm just going to clear everything out of here, and we'll just use a very simple example of 1, 2, and 3. Okay, and we want to figure out what is our combinations going to be for 1, 2, and 3. So we're going to have our empty slate, right? Now, what are our options at the first level? Well, we can add 1, we can add 2, or we can add 3, right? Now, what are our options at the second level? Well, we can add 1 and 2, or have 1 and 3. We can have 2 and 3, and then we have 3, right? And then what about the next level? Well, we have 1, 2, 3. 1, 3 goes to the end, so we have 1, 3. We have 2, 3, and then we have 3, right? So how many different options do we have? Well, we have nothing in the slate. We have 1, 2, and 3. Let me actually use a different color here so it's a little more clear. We can have an empty slate, so nothing. We can have 1, 2, and 3, 1 and 2, 1, 3, 2, 3, and 1, 2, 3. So how many do we have here? Well, we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, and 8, right? So relative to the input, what's happening? Okay, we're having 2 to the n. Okay, where n is the size of the input. So if we do 2 times 2 times 2, that's going to give us 8, right? And then what else do we have to do? We have to do one more thing. We have to do times n, because at the end, at the bottom of our tree, the leaf level, we're going to do a linear scan, right? So here we want to do 2 to the n times n. Okay, so our time is going to be O of 2 to the n times n, worst case. Now what about space, right? Well, if we're going to do all combinations, it's going to be the same thing. The space, the result for all combinations is going to be O of 2 to the n, right? And now we also have to factor in the call stack, right? How big is the call stack going to get at any point? Well, when we get to the leaf level, worst case, our call stack is going to be n, right? So this will also be 2 to the n times n on space. So it's terrible for time and space complexity, and that's why it's so important to use backtracking to rule out any candidates that might not be a potential for our result. And we just clip it right there, and we don't go down the rest of the tree, because this is so inefficient when we try to, you know, go through if we have to make up the entire tree. This is horrible on time and space. So that's why it's really important to understand backtracking, why it's so useful, why it's so important, and yeah, and it just adds a lot of efficiency to these types of problems. Okay, so that is Leetcode number 40, combination sum 2. I highly recommend, if you're still confused on this, to check out the other questions in this playlist. They are all using a same template that you know, we can just make slight modifications to and solve any type of problem that's dealing with combinations, permutations, or subsets. So it's very powerful. Okay, hope you enjoyed it, and I'll see you all on the next one.